In this video, we are going to take the ideas that we have been learning over the past several videos, and we're going to put them all together and see if we can come up with the sketch of a curve. Right? So we're going to think about ideas like increasing and decreasing, vertical asymptotes, horizontal asymptotes, slant asymptotes. We'll think about domain and range, inflection points, all those different things. We're going to try to come up with what's going on, right? Concavity, all those fun things. All right, so here are the guidelines that we're going to look at for curve sketching. So first thing we'll do is we'll see if we can identify the x and y intercepts. Sometimes they won't exist, but we will go through and see that. We will identify the domain, and then if it's readily available, we will identify the range. Sometimes we'll skip over the range, but we'll at least make a glance at it, see if we can identify anything about the range. Is it always positive, always negative, or could it be positive or negative, or is it unclear? We want to identify any points of discontinuity, right? So do we have a hole in the graph? Do we have vertical or horizontal asymptotes? Identify critical numbers. So those are where the derivative is 0 or where that derivative does not exist. And then we use those to find those intervals of increasing and decreasing. We use those critical numbers along with the points of discontinuity to split that up. Identify any inflection points or and then those intervals at which the function is concave up and concave down, right? So the inflection points. And then we think about the end behavior of the graph, right? So the limit as x goes to infinity, the limit as x goes to negative infinity. So we're going to go through all of those things. That's the idea when we are sketching the graph of a function. All right, so let's jump straight into an example. Here we have f of x equals 2 times x squared minus 9 over x squared minus 4. This will factor on top to x plus 2 times x plus 3 times x minus 3. And on bottom, it will factor into x plus 2 times x minus 2. If we want to find our x-intercepts, right? So step 1, we'll find the x-intercepts. How do you find an x-intercept? Well, you're going to set the y value equal to 0. And so that would tell us that that top part, 0 is equal to 2 times x squared minus 9, which we saw up above that factored. So 0 is equal to 2 times x plus 3 times x minus 3. If we set each one of these pieces equal to 0, so 2 is never equal to 0, x plus 3 equals 0 when x is negative 3, x minus 3 is equal to 0 when x is equal to 3. So x equals 3 and negative 3, those are going to be x-intercepts that we have. We will also identify any y-intercepts. So for the y-intercepts, we find those by plugging in 0 for the x. And so y is equal to 2 times 0 squared minus 9 over 0 squared minus 4. And if we solve that, we end up with y is equal to negative 18 over negative 4, which is 9/2. So y equals 9/2. That is our y-intercept. Right? So that's the first step in our process, right? So we identify the x and y intercepts. Then we are going to identify the domain. So our domain typically when I'm thinking about domain, I ask myself the question, are there any values of x that would cause problems that don't allow us to find, to evaluate the function? And we're going to have issues if we divide by 0. So any values that make that denominator 0, those are going to be bad news. And so our domain is going to be all real numbers except for -2 and +2. Right? So if we were to plug -2 into this denominator, we would be dividing by a 0. If we plug +2 in, we would also get a 0. So both of those values would make that denominator 0. So those values will not be in the domain of that function. Great. The range, it's not immediately clear what's going on with the range, so I'm just going to skip over that. We could get negative values here. We can get positive values. It's not abundantly clear what's going to happen with that range. So that was our second step. We then want to identify points of discontinuity. So for our points of discontinuity, well, those places that were not in the domain, both 3 and -3, those are going to be points of discontinuity. What type of discontinuity are those going to be, though? Well, when we plug in, sorry, not 3 and -3, 2 and -2, goodness. Right. So 3 and -3, those are definitely defined. Those are X-intercepts. 2 and -2 are points of discontinuity. What type of discontinuity are those? Well, they're both going to be vertical asymptotes because they make the denominator 0, but they don't make the numerator 0. So when we plug those in, we're not going to get any kind of cancellation. So it's not going to just be a hole in the graph. It's going to be a vertical asymptote. So we have vertical asymptotes. At x equals -2 and x equals 2. So those are our points of discontinuity. So far, we are up through the first 3 steps. So next we want to identify the critical numbers and the intervals over which the function is increasing and decreasing. So to find those critical numbers, we are going to find our derivative. So here we're going to have a quotient rule that happens. So we have low d high. The derivative of the top is going to be 2 times 2x minus high d low, square the bottom, and away we go. And if we go through and multiply things out, we're going to have, let's see, so this was a multiplication sign right there. So we have 4x cubed minus 16x minus 4x cubed plus 36x all over x squared minus 4 squared. The 4x cubes will cancel out, and so we're going to be left with just 20x on top and x squared minus 4 squared on bottom. So when is our derivative equal to 0? Well, it's going to be equal to 0 if that top part is 0 and the bottom part is not 0. So if 20x is equal to 0, so if x is equal to 0, we're going to have a critical point, a critical number. The derivative does not exist if our denominator is 0. If you were to factor that, we would find that's going to happen when x is equal to -2 and 2. Now, those would not be critical numbers because they were not in the original domain of the function, but they are still places where we're going to break this up when we look at a sine chart for our derivative. So, now we're going to create a sine chart for our derivative. So we'll go from -infinity up to -2. We will go from -2 to 0, from 0 to 2, and from 2 to infinity. Plug in some value between -infinity and -2, so like -10, you could throw that in there. We're going to throw that into the first derivative. So I would typically look at this here. Observations I would make is that denominator, since it's being squared, that denominator is always positive. So if we plug in something like -10, we have 20 times -10 is a negative, divided by a positive. So that's going to result in a negative value. Choose something between -2 and 0, like -1, and we will still get a negative value there. And then we'll get positive values if we're between 0 and 2, and between 2 and infinity. So what does this tell us? Well, this tells us that f is increasing on -infinity to -2. Nope. It's increasing on 0 to 2, along with 2 to infinity. Now, you might be tempted to say, oh, it's increasing from 0 to infinity, but remember, 2 is a vertical asymptote, so it can be increasing and then take a jump way down and then start increasing again. And f is decreasing on the interval from -infinity to -2, along with -2 to 0. All right, so that was our fourth step. Next, we are going to do the same thing, except for now we're going to find an inflection point. So we're going to take our second derivative, set it equal to 0, find where it changes concavity. So for our second derivative, so recall our first derivative, we're going to use the cleaned up version of that. Was 20x over x squared minus 4 squared. So our second derivative, again we have a quotient rule, x squared minus 4 squared, low d high, times 20 minus high, 20x, d low. Here you're going to have a chain rule that happens when you take the derivative of that bottom. So we bring the power down, subtract 1 from the power, then multiply by the derivative of the inside, all over that denominator squared, x squared minus 4 squared, squared. And in the interest of time, I'm not going to show you all the steps. We have a lot of algebra steps that would happen here, but we will get -60 x to the 4th on top plus 160 x squared plus 320. And then on bottom, I'm going to leave that as x squared minus 4 to the 4th power. So that is our second derivative. What are we going to do with that second derivative? Well, we're going to find out where is it equal to 0. So it's going to equal 0 when negative 60 x to the fourth plus 160 x squared plus 320 is 0. How would you solve that thing? Well, there's a variety of ways that you could go about solving it. You could look to factor it. I'm going to use the quadratic formula, essentially. Now, typically we would say x is equal to something, but since this is a quartic, we have x to the fourth and an x squared here. We're matching that x to the fourth as being x squared plus 160x squared to the first. And so this will be a solution for x squared. And so we have x is equal to negative b, so negative 160, plus or minus square root of b squared minus 4ac. That is going to give us, the square root of that will give us 320, all over 2 times negative 60. And if we do that, we get x squared is equal to 4. Or we get x squared as some negative value, but since it's squared, it doesn't make sense to be the negative value. If x squared is equal to 4, then x is either plus or minus 2. Now, we might observe those are the same values that will give us 0 in the denominator. And so, when we look at this, we can do a sine chart. We're going to go from negative infinity to negative 2. Go from negative 2 to 2, and then from 2 on up to infinity. And now we are doing a sine chart for the second derivative. If we plug in a value smaller than negative 2, plug it into our second derivative here, then we will get as an output, we're going to get a negative value. So plug in any value between negative 2 and negative infinity. So negative 10, negative 8, negative 3, whatever you want to plug in. We'll plug in something between negative 2 and 2. So 0 is a nice value to plug in there. Again, we're plugging it into the second derivative. If we plug in 0, we'll get a positive value. If we plug in something larger than 2, we're going to get a negative value. So what does that tell us? Well, it tells us that f is concave up on negative 2 to 2. F is concave down on negative infinity to negative 2, along with 2 to infinity. Do we have any inflection points? Well, we might be tempted to say, well, here at negative 2, it changes from concave down to concave up, so we have an inflection point there, and it changes from concave up to concave down right here. However, recall, we have previously identified those as vertical asymptotes, so those won't be inflection points. All right, so then the next thing we want to do is we want to identify the end behavior, and then we will be able to graph this thing. All right, so let's add another page. Our end behavior, we're looking at the limit as x heads towards infinity of 2 times x squared minus 9 over x squared minus 4. If we were to evaluate that, notice that the power on top and power on bottom are the same power, so that limit is going to be the ratio of the leading coefficients, so that limit is 2. Similarly, the limit as x approaches negative infinity is going to be that same value. So we get a horizontal asymptote of y equals 2. All right, so now let's put it all together and graph this thing. So when we put this thing together and graph it, at 2, we had a vertical asymptote. At negative 2, we had a vertical asymptote. At y equals 2, we have a horizontal asymptote. We had at, let's see, as intercepts, we had an x-intercept at 3 and negative 3, and a y-intercept at 9/2 at 4.5. So at 3, we'll have an x-intercept. At negative 3, we have an x-intercept. At 9/2, we have a y-intercept. We identified our function was decreasing here and here and increasing here and here. We had concave up everywhere from negative 2 to 2 and concave down outside of that. And so what we're going to end up with is, this is concave down and decreasing. It's concave up here. It's decreasing from negative 2. From negative 2 to 0, it's decreasing. And at 0, it starts to increase. It's still concave up. And then we are concave down and increasing here. And so that is what we have. So these curve sketching problems, they are pretty intense because they ask us to do pretty much all of the things, but we're able to go through and do that. Come back for our next video when we will look at another example. We'll see you there.